fuel control. What I want to do here is go into Lambda mode, and I'm going to be doing auto mode wideband and clicking OK. The number of banks here will leave at 1 bank. The bank source Lambda average, I'm going to change that not from Lambda average, but to Lambda 1 because we're not averaging banks, we just have a single bank and a single sensor. The ECT lockout, I'll lower this down to 32, I think is the lowest we can run. We can go into closed loop right away when we fire off the engine. Now the startup timer lockout, this depends on if you're running an internal built-in wideband with something like a Fury, or if you're running an external controller here like I'm dealing with this X series gauge. The X series take about 30 seconds for the heater cycle to warm up and for the sensor to come online so they start to register and read properly. We don't want our closed loop turning on until the gauge actually goes live and the heater circuit completely warms up and everything is 100%. Because if it looks at a signal that's not going to be valid, it'll make incorrect corrections against our main field table in terms of what the closed loop correction is doing. What I want to do is change this from 5 seconds to, let's say, 30 seconds. That should be good for an X series. The map lockout, I want this to apply at full throttle and part throttle. I'm going to set this to really high at something like 400 kPa. The RPM lockout, I'll say go out to 9,000. I want this to apply at part throttle and full throttle, so we want it to go high RPM. Low RPM lockout, I'll say 500. That's where it starts its control from. TPS lockout, we're going to set this to 100. Now the TPS delta and map delta lockout, this is the rate of change in throttle or load in order for it to kick out a closed loop. When we have a transient or acceleration enrichment event being applied, we have a momentary burst of airflow. And the wideband a lot of times can't sample quick enough and it gives us skewed data. We don't want the closed loop chasing a bad wideband signal or registration reading. That's why we use these as a buffer. As soon as the acceleration enrichment's tipped in and applied, we turn off the closed loop. So these values should be good. We can leave those alone. Trim limit tables right now, this is going to either turn on or turn off the trim tables where we can be specific of how much we're allowing to either add or subtract to different load or RPM ranges. I usually like to keep this simple with the closed loop, so in this situation I can leave this off. If I find that we're having odd behavior, I can turn this on and populate a table out. Again, it'll give me a 3-dimensional trim table that'll look at load and RPM of how much I want to trim. So if maybe at idle I only want to trim plus or minus 5%, but at part throttle and full throttle I want it to go out to 15%, it'll give me a bit more flexibility. Let's keep things simple right now, and let's keep our min and max values at plus or minus 15 or 20. That'll give us a decent amount of adjustments once we get things going and get up and running. Now, what I'm going to do at this point is just set my min and max levels at 0. I'm doing this specifically because I want to make sure when we get the engine fired up and running and do our sensor check in the next video, that the wideband is reading properly and that we don't have any kind of erratic behavior because we've turned our closed loop control on. Big injectors are difficult to control, so as we're turning on closed loop, that can start to further complicate the tuning process. What I want to do here is simplify it. When we're creating our base file, we'll leave this off, we'll come back in here and repopulate this to actually start to do something when we get the engine running and we verify that the engine is stable and can hold its own idle. Then we can introduce the closed loop correction. Very important with big injectors. Coming down here below, we have update rate and gain control, which are found right here. And then we also have our long-term fuel trim. We'll leave that off for right now. We'll get into that when we do the part throttle and get everything fired up and running. Looking at our loop control rate, this is the update rate, how quickly the wideband signal feeds back into the PID calculations that are going on in the background. At high engine speeds here, I usually ramp up this rate relatively quick. We'll say something like, I think 15 is the limit if I remember correctly. No, 10 is the limit. So when we're dealing with the G4 Plus, we could have, I think 20 is the highest rate here. On the G4X here, 10 looks like it's the highest rate. I always forget going back and forth between the two. 0 to 1,000 here, we'll go and have a slower update rate because the engine cycles aren't happening as quick. We don't need the wideband to feed its signal in as fast. So I'll say something like 2 right here. But off idle, 1,000 RPM to 6,000, we'll do Shift H and we'll speed up. As engine speed speeds up, we'll speed up that feedback rate and feed it back quicker. So the higher the value, the quicker it's feeding back into the PID calculations, looking at the error between our Lambda sensor, the actual reading, and then the target Lambda. The closed loop gain allows us to essentially turn up or down the sensitivity to how quickly the closed loop correction is making its adjustments. If we allowed a 20% window here, adding or subtracting, it's how quickly it's able to add that or take it away. We need to go and be relatively aggressive with these values here. If we're looking at our large error, so 0 means we have no error. we generally want to have our zero error being 0. But as we're going here and the error starts to grow, we need to be more aggressive with how we're changing things. I'm going to say here at the highest error in the table, I'll go here and have a factor of something like 10. And then here going across. So as the error grows, I'll get more aggressive with the gain or how quickly it's allowed to add or subtract this percentage trim. I'll do Shift H and we'll just populate that through the table, and we can come back in here and adjust these as needed, but these are going to be good starting points. The next thing we need to do is jump into our air fuel Lambda target table. And this is going to be setting the target air fuel that we want to run the engine at. Now, something specific with this engine, with these injectors, we need to make sure that we are targeting a richer mixture at idle conditions, because the injector won't perform as linear at 14:7, 15:1 as it would at something like 13:1. By going and increasing the pulse width, it allows it to run further away from the nonlinear operation zone, even with that short pulse width adder values that we.
Thanks for checking out our teaser clip. If you want to see the rest of this video and more than 500 hours of current EFI training we have to offer, make sure you click right here. If you want to go and check out more teaser clips from this training course, click here, and you don't want to miss any of the videos we're going to be releasing on this channel, so make sure you subscribe and click here. Thanks for watching, and I'll see you guys later.